The rapid pace of technological advancement in the 21st century has ushered in an era where satellites play an indispensable role in global communications, navigation, environmental monitoring, scientific research, and even national security. As the demand for these services continues to grow, so too does the number of satellites being launched into orbit, particularly into low Earth orbit (LEO). The question of how many more satellites can safely occupy these orbital regions without increasing the risk of collisions has become a topic of intense debate. However, based on the data and analysis available, it can be argued that there is virtually no limit to how many more satellites can be safely added to orbit.
As of 2024, approximately 10,000 active satellites are orbiting Earth, with the majority concentrated in LEO, which extends up to 2,000 kilometers above the planet's surface. LEO is particularly attractive due to its proximity to Earth, which offers lower latency in communications and higher resolution imaging for Earth observation satellites. Companies like SpaceX, with its Starlink project, and other private and governmental entities have launched thousands of satellites into LEO to provide global internet coverage and other services.
Despite concerns about space becoming crowded, the data suggests that the orbital environment is far from reaching its capacity. The space available in LEO is vast, and the current number of satellites represents only a fraction of what could potentially be accommodated. To illustrate this, it's important to consider the sheer volume of space in LEO. The volume of a spherical shell, which is what LEO essentially forms around the Earth, is calculated using the formula V equals 4/3 pi r underscore 2 caret 3 r underscore 1 caret 3, where r underscore 2 is the outer radius, 2,000 kilometers above the Earth's surface plus the Earth's radius, and r underscore 1 is the inner radius, the Earth's radius, approximately 6,371 kilometers. This gives us a volume of approximately 72 trillion cubic kilometers in LEO. Given this immense space, the current population of around 10,000 satellites is minuscule.
One of the primary concerns with increasing the number of satellites is the risk of collisions. It's often suggested that as more satellites are added, the likelihood of collision increases. This idea is based on the principle that the probability of a collision is proportional to the square of the number of satellites. However, even with this exponential relationship, the current and projected numbers of satellites remain well within manageable limits. To understand why, consider the following calculation. If the number of satellites in LEO were increased to 100,000, the probability of collisions would indeed rise. The probability of a collision between any two satellites in a given time period can be expressed as p underscore collision equals kxn squared, where k is a constant that depends on the specific orbital environment and the size and speed of the satellites, and n is the number of satellites. If we increase n from 10,000 to 100,000, the probability increases by a factor of 100. However, this increase is not as alarming as it might seem at first glance.
One of the most significant factors enabling the safe addition of more satellites is the development of highly effective CAS. These systems are designed to detect potential collisions well in advance and autonomously maneuver satellites to avoid them. With CAS technology improving rapidly, the effective management of satellite populations is becoming increasingly feasible. Assuming a CAS effectiveness of 90%, even a substantial increase in the number of satellites would not lead to a significant increase in collision risk. For example, with 100,000 satellites in LEO and a 90% effective CAS, the adjusted collision probability can be recalculated as p underscore adjusted collision equals 0.10 times 1,000 000/10 000 caret 2 times p underscore collision equals 10 times p underscore collision. This calculation illustrates that even with a tenfold increase in the number of satellites, the risk remains controllable. This underscores the potential for virtually unlimited expansion in satellite numbers, provided that collision avoidance systems continue to be refined and implemented effectively.
To put the capacity of Earth's orbit into perspective, it is useful to compare the satellite population to the number of vehicles on Earth. Currently, there are approximately 1.5 billion vehicles globally. This figure dwarfs the number of satellites in orbit and highlights the relative sparsity of objects in space compared to objects on Earth's surface. If we were to hypothetically reduce the global vehicle population to match the current number of satellites in LEO, the impact on collision rates would be dramatic. For instance, reducing the vehicle count to 10,000 would almost entirely eliminate the possibility of collisions. The current rate of vehicular collisions on Earth is about 20,000 per day. However, with only 10,000 vehicles on the planet, this rate would drop to near zero, showcasing how much less crowded LEO is compared to Earth's surface. Let's extend this comparison by considering a hypothetical scenario where we only had 2 million vehicles on Earth, a figure comparable to a low number of satellites in orbit. The number of daily collisions would be negligible. By scaling this up to a satellite context, it suggests that even with a significant increase in the number of satellites, the collision rate would remain low.
Another interesting comparison is the number of aircraft in the skies. At any given moment, there are approximately 10,000 aircraft flying worldwide. This number parallels the current number of satellites in LEO, providing a useful benchmark for understanding traffic density in different domains. The management of air traffic involves sophisticated systems that track the position, speed, and altitude of each aircraft, similar to how satellite trajectories are monitored. Despite the large number of flights, the incidence of mid-air collisions is extremely low, thanks to effective air traffic control and technologies such as TCAS, Traffic Collision Avoidance System. The comparison between aircraft and satellites is apt because both operate in environments where safety and precision are paramount. The low incidence of aircraft collisions demonstrates that with proper management and technology, dense populations of vehicles can be safely managed, whether they are in the air or orbiting the Earth.
While the majority of satellites currently reside in LEO, it is important to remember that Earth's orbit is divided into several layers, each with its own unique characteristics and capacity. Beyond LEO, there are medium Earth orbit (MEO) and geostationary orbit (GEO), which offer even more room for satellite expansion. Medium Earth orbit (MEO) ranges from 2,000 to 35,786 kilometers above Earth's surface. This region is primarily used for navigation systems such as GPS, Galileo, and GLONASS. The lower density of satellites in MEO compared to LEO means that there is ample space for additional satellites without significantly increasing the risk of collision.
Geostationary orbit (GEO) is located approximately 35,786 kilometers above the equator. Satellites in GEO remain in a fixed position relative to the Earth's surface, making this orbit highly valuable for communication satellites. While GEO has more limited capacity due to the need to space satellites carefully to avoid interference, the risk of collision is minimal due to the relatively low density of satellites and the use of CAS. In both MEO and GEO, the potential for increasing the satellite population is substantial. MEO, in particular, has vast expanses of space that are currently underutilized, offering significant potential for expansion. GEO, while more crowded, still has room for additional satellites, especially as new technologies emerge that allow for more precise positioning and collision avoidance.
The current rate of satellite production and launch is unprecedented. Companies like SpaceX, OneWeb, and Amazon's Project Kuiper are planning to launch tens of thousands of satellites over the next decade. SpaceX, for example, is launching around 60 satellites per mission, with plans to deploy up to 42,000 satellites for its Starlink constellation alone. At this rate, the global satellite population could increase by tens of thousands in just a few years.
Assuming the current rate of satellite production and launch, it's possible to estimate how long it would take to reach certain milestones. For example, if we aim to increase the satellite population by 90,000, and assuming an average production and launch rate of 1,500 satellites per year, it would take approximately 60 years to reach this target. Time equals 90,000 satellites slash 1,500 satellites slash year equals 60 years. However, it's important to note that advancements in production techniques, launch technologies, and international cooperation could significantly shorten this timeframe. As technology improves and economies of scale are realized, the rate of satellite production is likely to increase, potentially allowing us to reach these numbers much sooner.
The future of space is expansive, and the sky is not the limit. It's just the beginning.